In section 5.2, we deal with perpendicular and angle bisectors. But wait, you might be asking, didn't we already go over what perpendicular and angle bisectors are? Why yes we did. But we are going to be taking each of them one step further in this section. First, some vocabulary. A point is equidistant from two objects if it is the same distance from the objects. The name just about gives it away. Equidistant is just equally distant. Let's say we have an eagle. And that eagle is spying two possible choices for lunch. Being a lazy eagle, he tries to decide which one is closer. He finds that they are the same distance away. So he would say that the eagle is equidistant from the two mice. That is the meaning of equidistant and how it might be used. We have certainly gone over what a perpendicular bisector is before. Here I have a red line which is both perpendicular and bisects line segment AB. So that red line is definitely a perpendicular bisector of line segment AB. But let's look a little closer. At the point of intersection there is a point which I have drawn as blue. It should be obvious, but that point is equidistant from point A and point B. It is the midpoint of line segment AB. The segments have even been marked as congruent in the picture, so hopefully it is obvious that the blue point is equidistant from point A and point B. But the very nature of a perpendicular bisector is that it is right smack dab in the middle of the line segment. Not just one point, but all of them. So here's another point on the perpendicular bisector. If I measure out from that orange point, I would see that it too is also equidistant from point A and point B. What do you suppose is true about any point on the perpendicular bisector? It doesn't matter which point you choose, every point on the perpendicular bisector is equidistant from point A and point B. Even the points that are below line segment AB work. Although it's getting a little crazy here with all the tick marks I have. The perpendicular bisector is right in the middle of the line segment. Every part of it is right in the middle. Thus every point will be equidistant from either endpoint of the line segment. That brings us to the theorem. The perpendicular bisector theorem says exactly what I just demonstrated. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. In practice, you aren't going to be using this theorem in a proof. Rather, you will use them in problems like this. Here I have a picture where line CD has been shown to be a perpendicular bisector. We have 2 points that are labeled that sit on that perpendicular bisector, namely point C and point D. So if you notice that you have that perpendicular bisector, you can make conclusions. First, since point C is on the perpendicular bisector, you know that point C is equidistant from point A and point B. We can mark those line segments congruent. This means that triangle ABC is isosceles. Similarly, since point D is also on the perpendicular bisector, you know that point D is equidistant from point A and point B. We can mark those line segments congruent too. This means that triangle ABD is also isosceles. That is how we are going to be extending our knowledge of perpendicular bisectors. You need to be able to identify that a perpendicular bisector is happening, and then you can probably mark some line segments congruent. The converse of the perpendicular bisector theorem also works. Just like the perpendicular bisector theorem, we won't be using it in a proof. We made sure you knew the difference between the isosceles triangle theorem and the converse of the isosceles triangle theorem because they would be used in proofs. These won't, so you don't need to worry about keeping straight which is a theorem and which is the converse. But the converse does work. If you know a point is equidistant from the endpoints, then you know it's on the perpendicular bisector. That's fine and all, but you should actually already know that. In section 4.5 we went over isosceles triangles, and you'll notice that this converse starts out with an isosceles triangle. It doesn't actually say it's an isosceles triangle, but it ends up meaning the same thing. Since point P is equidistant from point A and point B, it makes triangle ABP isosceles. Now in section 4.5 we went over the idea that they are symmetric shapes. There is an axis of symmetry in each isosceles triangle, and that it would also be extremely common for us to split those isosceles triangles down the axis of symmetry like this. By splitting down the axis of symmetry, all of the corresponding parts on either side are congruent. You'll notice that the perpendicular bisector is part of that information. So this converse is actually something you already should have been able to figure out. It's just packaged and brought to you in a new way. Mathematics will end up doing that a lot to you over your math career. One little concept to cover before we move on to the next theorems. Let's say I wanted to know how far it was between Los Angeles and Chicago, if I flew directly there. For those of you bad at geography, Los Angeles and Chicago are the two red stars highlighted on the map. I just want to know how far it is so I know if I have enough fuel to make it. Seems simple enough, right? We just want to know the distance. But we wouldn't take a scenic route to figure it out. I wouldn't first head up to Seattle, then on over to Salt Lake City, pop on over to Denver, mosey on down to Dallas, move on up to Kansas City, freeze my buns off in Minneapolis, and then finally get to Chicago. Side note, I wonder how many of you actually could have named all those cities without my help. But the point stands. The distance is not a meandering amount. The distance between two things is the shortest distance between them. No scenic flying allowed. Keeping that in mind, now I want to find the distance from a point to a line. Just like the distance from Los Angeles to Chicago is the shortest distance, The distance from a point to a line is also the shortest distance from that point to the line. It just so happens that the shortest distance from a point to a line is the length of the perpendicular segment from that point to the line. You will see that quite a few times in geometry. When we want to find the distance to something, the perpendicular is always involved. We will use this idea with the angle bisector stuff coming next. We have definitely gone over angle bisectors before. Here the red ray has been marked as an angle bisector of the larger black angle. Just like a perpendicular bisector is right in the middle of a line segment, an angle bisector is right in the middle of an angle. Just like every part of a perpendicular bisector is in the middle of that line segment, every part of the angle bisector is right in the middle of the angle. So you can choose any point that you want that is on the angle bisector. Every one of them is equidistant from the sides of the angle. To show that these points are equidistant from the sides, you show both the line segments are congruent and also that they are perpendicular, just like I have done here. That's where the whole discussion about distance to a line comes in. The distance between each of those points to the line is going to be the shortest distance, which will always be the perpendicular. So those right angle marks are how mathematicians show that we are dealing with the distance to the line. You'll need to get used to those markings showing distance. They will come up quite a few times this year. This leads us to the theorem. The angle bisector theorem says that if a point is on the bisector of an angle, then the point is equidistant from the sides of the angle. That's exactly what I demonstrated. Just like the perpendicular bisector theorem, the converse of the angle bisector theorem also works. With the converse, you just start off with the fact that the point is equidistant from the sides, and the only way that is possible is if that point is on the angle bisector. That should make sense. If the point is equidistant from the sides, then it is right in the middle. That's where the angle bisector is, right in the middle. I know you're going to be depressed about this, but none of the theorems or converses this section will be used on a proof. So you don't need to keep straight whether something is a theorem or the converse.